Now we want to see how derivatives come into play for functions of several variables. In Calculus 1, we learned that derivatives measured the rate of change of one variable with respect to another. Typically, we had those variables given in the function. It's also called the slope of the tangent line. In functions of several variables, however, we can have derivatives defined to be with respect to any of the independent variables. Very similar to the definition from Calculus 1, the difference quotient looks like this. And you notice that the y in this case is just a y. The change, the delta, is on the x. So we are changing the x and looking at what happens when we change only the x. We call this the partial derivative with respect to x when we're changing only the x. And the symbols we use for that are the f, meaning the function, with the subscript of x. That's read the derivative of f with respect to x. And we have this symbol, which we use for our partial derivative. Resembles symbols that we learned in the Greek alphabet, but it's not a Greek letter. It's just a symbol that's been made up to mean the partial derivative. Also, treating x as a constant, we get the partial derivative with respect to y, which we abbreviate like this. Now, the derivative rules are a lot like the derivative rules we learned in Calculus 1. For example, the derivative of 3x squared by the power rule would be 2 times 3 x to the first. Now, in partial derivatives, we have, in this expression, we're doing the partial derivative of y times x squared with respect to x. We want to, in our mind, envision the y just like it's the 3. So this is basically like 3x squared. We're doing the derivative of some constant times x squared. Well, by the power rule, that's 2 times the constant times x to the first, which in this case would be 2 times y times x to the first. Here's another one from Calculus 1. The derivative of sine of anything would be, by definition, cosine of that, when in the chain rule tells us do the derivative of the argument. So this one would be the cosine of 2x times the 2. Well, if we have a similar expression, sine of x times some constant, and we're doing the derivative with respect to the x, it's going to be the sine of x times the constant times the derivative of x times the constant. Now that comes out to be just a y cosine xy. Here's another one. The derivative with respect to y of e to the 3y would be e to the 3y times the derivative of the 3y. And here's what it would look like with functions of two variables. We got x's and y's. When we look at that, we see the x just like a number, a 3 or a 2 or anything else. So we're looking at the derivative of e to some constant times y. That derivative would be e to the constant times y times the derivative of the constant times y. Now here's the paraboloid, z equals negative x squared minus y squared, and I've located the point 1, 1, negative 2 on the paraboloid. Now the partial of f with respect to x would just be negative 2x, the y is a constant, so that derivative would be 0. Substituting the 1, 1, substituting 1 for x, we get negative 2 times 1, or negative 2. So the slope in the x direction at that point would be a negative 2. Now I've drawn a graph of it here for you. There's the point, 1, 1, negative 2. We're looking here along the x, z axis. The slope of that blue line is negative 2, the slope in the x direction. Here's the partial with respect to y, which again, the x is a constant. The derivative of this term with respect to y would be negative 2y. Plugging in the 1 for y, we get the slope in the y direction of negative 2. Here's a graph of the slope in the y direction. Again, you can see we're looking along the YZ axis. Now here I've drawn the graph of both of those lines, the tangent line in the x direction and the tangent line in the y direction. Now we'll talk about this in the very near future, but remember, two lines determine a unique plane. So guess how we can find the tangent plane? So here we're going to practice doing the derivative. So first off, notice we've got two terms. We'll use the product rule. We do the derivative with respect to x of the x squared. We copy down the e to the xy. We copy down the x squared. And then we do the derivative of e to the xy. Now the derivative of e to the xy is just like the derivative of e to the 3x, or e to the 2x, or e to the 5x. It's e to the constant times x times the derivative of the constant times x. In this case, just e to the xy times y. Similarly, we'll just kind of shift gears in our head. We still have to use the product rule on this one. However, since we're doing the derivative with respect to y, the derivative of x squared is going to be a 0. Copy down e to the xy, copy down the x squared, and very similar to the first one, the derivative of e to some constant times y is e to the constant times y times the derivative of the constant times y, which would be the constant, in this case x. And so there's our partial derivatives. We can do higher order derivatives. You notice in this one we're doing what's called the second partial of x. That just means we've done the derivative of x with respect to x, and then we did the derivative of that with respect to x. Now this is the other symbol that says the same thing, the second partial of f with respect to x both times. Now this is called the mixed partials. In the first one, we're doing the partial with respect to x, and then we're taking that and doing the derivative with respect to y. Second one, we're doing it the reverse order. Derivative with respect to y first, then the derivative of that with respect to x. And that's, of course, what this other symbolism says. And here is the second partial of y. And it simply says you do the derivative with respect to y, and then do the derivative of that with respect to y again. So let's go through the derivative of this one. First off, notice that if we do the derivative with respect to x, we will split this apart into the two terms. The derivative of the first one with respect to x, that means e to the 3y would be a constant. The derivative of a constant times x is just the constant. So that derivative would be e to the 3y. The derivative of sine of anything would be cosine of that same thing times the derivative of the argument for the cosine. Now we're doing the derivative with respect to x, so the derivative of 2x would be a 2, and the derivative of 5y would be 0. So that gives us our 2 cosine 2x minus 5y. Now if we do the derivative of that with respect to y, here's the first term, and we're doing the derivative. Y is our variable. We will copy down the x, and the derivative of e to the 3y would be e to the 3y times the 3. And same thing on sine 2x minus 5y. The derivative of sine of anything is cosine of the same thing times the derivative. The derivative of 2x would be 0. The derivative of negative 5y would be negative 5. So now let's do the derivative of this with respect to x. The derivative of e to the 3y, since there's no x in it, would be 0. So to do the derivative of 2 cosine 2x minus 5y, we will copy down the 2. The derivative of cosine would be negative sine, still 2x minus 5y. Then we have the derivative of the 2x minus 5y. Now we're doing the derivative with respect to x, so the derivative of 2x would be 2, and the derivative of 5y would be 0. So we end up with 2 times 2, or 4, sine 2x minus 5y. And likewise, if we take the partial with respect to y, and then do the derivative of that with respect to y again, here's this term. Since we're doing the derivative with respect to y, the 3x is just a constant. The derivative of e to the 3y would be e to the 3y times the derivative of 3y. Now that comes out to be the 9x e to the 3y. And the derivative of 5 cosine 2x minus 5y, if we copy down the 5, derivative of cosine would be negative sine. Leave the 2x minus 5y alone. Do the derivative of 2x minus 5y. Now 2x doesn't contain any y's, so the derivative of 2x would be 0. The derivative of negative 5y would be negative 5. So we end up with a negative times a negative times a negative, which would be a negative 25 sine 2x minus 5y. Now, as far as the mixed partials, we're taking what we had in the very beginning, the partial with respect to x, and then we're doing the derivative of that with respect to y. So the derivative of e to the 3y with respect to y would be e to the 3y times the 3. So that would give us our 3e to the 3y. If we copy down the 2, the derivative of cosine, negative sine, and then the derivative of 2x, since we're doing the derivative with respect to y, would be 0. The derivative of negative 5y would be a negative 5. So we end up with a negative and a negative, which is a positive, 10 sine 2x minus 5y. And the last one, we're taking the partial with respect to y, which we got in the beginning, and we're doing the derivative of that with respect to x. So we'll copy down the 3e to the 3y. That's the coefficient of x. We'll copy down the 5. The derivative of cosine is negative sine. And then we'll do the derivative with respect to x. Derivative of 2x would be 2. Derivative of 5y would be 0. That comes out to be negative and a negative, which is positive 10 sine 2x minus 5y. In the last example, we've got w, which is a function of x, y, and z. So we've got a function of 3 variables. In the first one, we're doing the derivative of w with respect to x. So again, we will split this apart. Here are our 4 terms. We're doing the derivative of this one with respect to x. That means the y is a constant. Let's copy down the y and do the derivative of x squared. On the second one, we're doing the derivative with respect to x. There's no x in there. This is a constant. The derivative of any constant would be 0. We're doing the derivative with respect to x. The derivative of 43x would be 43. We're doing the derivative with respect to x. The last term has no x in it. That means it's a constant. The derivative of any constant is 0. So there's our derivative of w with respect to x. Now, the derivative of w with respect to y. Now, again, we're going to take the first term. We're doing the derivative with respect to y. The x squared is a constant. We will copy it down. Derivative of y would just be a 1. So the derivative of x squared y would be x squared. Doing the derivative with respect to y, we'll copy down the 10 z cubed. We'll do the derivative on y squared. That would be 2y. 43x has no y in it, so the derivative of 43x would be 0. We'll copy down the negative 7. The derivative of tan of anything would be secant squared of that times the derivative of 4y. So there's our derivative. We can simplify some. last one, the derivative with respect to z. Here's our first term. There's no z in it. The derivative would be 0. Here's our next term. We'll copy down the negative 10y squared and do the power rule on z to the 3. That would be 3z squared. Next term has no z in it. Derivative would be 0. Next term has no z in it, and the derivative would be 0. So there's our derivative with respect to z.